Welcome to Jeremy's IT Lab. This is a complete course for the CCNP ENCOR, Enterprise Core exam. This course will cover all topics you need to know to pass the ENCOR exam. In this video, we will look at ICMP, Internet Control Message Protocol. ICMP is something I'm sure you've heard of during your CCNA studies. For example, when learning about ping, which uses ICMP echo request and ICMP echo reply messages. In this video, we'll go a little bit deeper and look at more of ICMP's role in supporting IP networks. Here's what we'll cover. First, I'll introduce ICMP and what it's used for in general. Then, we'll look at the different ICMP message types. We won't cover all of them, and there have been many more in the past that have been deprecated, meaning they have been removed from the ICMP standard. First, we'll look at a few messages in the error category: Destination Unreachable, Redirect, and Time Exceeded. Then, we'll look at a couple in the query category: Echo Request and Echo Reply. You should be familiar with the echo messages already. They're used in ping. Finally, we'll briefly look at ICMP v6. V6 doesn't mean it's the sixth version of ICMP, but rather that it's the version of ICMP used with IPv6. So, what is ICMP? ICMP is an auxiliary protocol that is an integral part of IP. By integral, I mean that IP devices must support ICMP, as stated in the RFC for ICMP. IPv4 is defined in RFC 791, and ICMP in RFC 792. I think that shows the connection between IP and ICMP. ICMP is defined in the next RFC after IP. ICMP messages are encapsulated in IP packets, with a protocol number of 1. That is referring to the protocol field of the IPv4 header. TCP is protocol number 6, and UDP is 17. However, although ICMP is encapsulated in IP packets, it is not considered a layer 4 protocol. It is considered part of IP. It is used by network devices to send error messages, make routing suggestions, and other functions. We'll see what it does when we look at the different message types. This is what the ICMP header looks like. It's quite simple, only 8 bytes. Let's go through each field. First, the type field indicates the type of ICMP message. For example, Destination Unreachable, Redirect, Echo Request, etc. Then, the code field is used to specify additional information for some message types. If it's a Destination Unreachable message, this code indicates why the destination was unreachable. The checksum field is used to check for errors in the ICMP header and encapsulated data. And finally, there is the rest of header section, which is 4 bytes in length. The contents of this section can vary depending on the message type and code, as you'll see when we look at different messages. So, this header is used to encapsulate the ICMP data, and the contents of the ICMP data depends on the message type. In ICMP error messages, the IP header and first 64 bits of the IP payload of the packet that caused the error are sent. It's a way of telling the device that originally sent the packet, this is the message that caused this error. And when using echo, meaning ping, the data in the echo request must be echoed back in the echo reply. Generally, it's just a series of ASCII characters with no meaning. But the device that receives the echo request must send the echo reply with the same data. If there are 500 bytes of data in the request, those same 500 bytes must be in the reply. However, note that not all ICMP messages encapsulate data. For example, a ping can have a 0-byte payload, which means it'll send the ICMP header only. Now let's look at some of the different ICMP message types. I'll introduce their general purpose and some extra details. Note that there are a few other ICMP message types we won't cover in this video, as well as many others which have been deprecated. For example, RFC 6633 is called Deprecation of ICMP Source Quench Messages, and RFC 6918 is formally deprecating some ICMP v4 message types. An example of a deprecated ICMP message type is traceroute. It used to be an ICMP message, but it was deprecated in RFC 6918. I'll make a short lesson about traceroute and how it works as a separate video. Now let's look at these different message types. First up, Destination Unreachable. I think the name makes the purpose of this message type clear. Destination Unreachable messages are used to inform a host that a packet couldn't reach its destination. And Destination Unreachable is ICMP Type 3. The code field indicates why the destination could not be reached. Here are a few of the codes you might find. For example, 13 at the bottom means communication administratively prohibited. A router will send that message if it drops a packet because of an ACL. We'll examine how Cisco routers use some of these Destination Unreachable messages in the lab video, so I won't get into details now. I already mentioned one of these in the MTU video. That is code 4, fragmentation needed and DF bit set. If a router needs to fragment a packet, but can't because of the DF bit, it will send a message like this. Notice at the end it states the MTU of the link, 1500, so the host can send smaller packets that fit within the specified MTU. Here's the ICMP header and data for a Destination Unreachable message. The type is 3, then there's the code and checksum, and notice the first half of the rest of header portion is unused, so it will be all zeros. Then the second half is next hop MTU. This field is only used with code 4, and this is how path MTU discovery works, as I already explained in the MTU video. It uses ICMP fragmentation needed messages. To summarize, the purpose of a Destination Unreachable message is to tell a host that a packet couldn't reach its destination. That's what the type of 3 means. Then the code specifies why it couldn't reach its destination. And finally, the encapsulated data says which packet couldn't reach its destination. As I pointed out before, in ICMP error messages, the encapsulated data is the IP header and first 64 bits, 8 bytes, of the IP payload of the packet that caused the error. In this case, the packet that couldn't be delivered. Okay, I think the purpose of this message is clear, but we'll explore some more details in the lab video, so be sure to watch that. Here's a simple demonstration of a Destination Unreachable message. R1 sends a packet, destined for PC3, to R1. R1 has a matching route, so it forwards the packet to the next hop, R2. However, in this case, R2 doesn't have a route matching destination 192.168.3.10, PC3, so it drops the packet. R2 then sends an ICMP Destination Unreachable message to PC1. In the lab video, we'll take a look at what code will be used in this case, when a router doesn't have a route for the packet's destination IP. By using the command showIPinterface, you can see if a router will send ICMP unreachable messages or not. By default, it is enabled on Cisco routers, as you can see in the output of the command. ICMP unreachables are always sent. Note that it's a per interface configuration. You can disable it with no IP unreachables on the interface. Now it says ICMP unreachables are never sent. In this case, R2 would simply drop the packet without sending a Destination Unreachable message back to PC1. You can also rate limit how often the router will send unreachable messages. The command is IP ICMP rate limit unreachables, then specify a time in milliseconds. This means the router will send unreachables at a maximum rate of 1 per the number of milliseconds specified. If you specify 1000 milliseconds, the router will only send 1 per second. This applies to all unreachable messages. But you can also specify DF in the command for don't fragment. This rate limits only code 4 unreachables, for packets that couldn't be fragmented. If you specify both, for example 1 per second for each, the router can send both one code 4 unreachable per second and one other unreachable per second, for a total of 2 unreachables per second. Next, we'll look at the redirect message type. Redirect messages are used to inform a host that there is a better route for a particular destination. This message type is used by routers to tell hosts to use a different router to reach this destination. And the ICMP type is 5 for redirect messages. The code field indicates the type of redirect. Here's a chart. Let's go through these briefly. 0 is redirect for network. It means the host should redirect not just for this destination IP, but for all destinations in the same network. Then code 1 is redirect for host. It means redirect all packets to this destination. You should send all packets destined for this destination IP to a different router, not to this router. Code 2 is the same as code 0, but only applies to packets with the same TOS value as the packet that caused the redirect message. And then code 3 is the same as code 1, but again, only for packets with the same TOS value as the packet that caused the redirect message. However, codes 0 and 2, which redirect for all destinations in a particular network, have been prohibited since RFC 1812. That is because of classless addressing. When using classless addressing, the actual network size of a destination is unknown. We can't assume, for example, that a class C address will be in a /24 network. Anyway, don't worry too much about these codes. Just know the general purpose of redirects. Routers use redirects to tell end hosts to send packets to a different router. Here is the format of a redirect message. The type is 5, and notice the rest of header section is just an IP address this time. That's the IP address of the other router. For example, R1 could be telling PC1, don't send these packets to me, send them to R2 instead. I'll demonstrate that in the next slide. Finally, notice that once again the encapsulated data is the IP header and first 8 bytes of the original IP payload, the packet that caused this redirect message to be sent. Let's see how redirects work. I took this example directly from some Cisco documentation about ICMP redirects. In this case, PC1 wants to communicate with server 1. Notice that PC1's default gateway is 192.168.1.1, R1. So, PC1 sends a packet, destined for server 1, to R1, its default gateway. R1 checks its routing table, and notices that R2 is the next hop, and forwards the packet to the destination via R2. It then sends a redirect to PC1, saying, instead of sending packets for this destination to me, you can send them to R2 instead. Its IP address is 192.168.1.2. Then, PC1 sends future packets for server 1 via R2 instead of via R1, its default gateway. So that's how redirect messages work. We'll take a look at this in the lab video too. You can check ICMP redirect settings with Show IP Interface. By default, they are enabled, as it says here. ICMP redirects are always sent. If you want to disable it, the command is No IP Redirects on the interface. And now it says ICMP redirects are never sent. In this case, R1 would not send a redirect message to PC1. So when PC1 sends packets to server 1, it will continue to send them via R1, instead of sending them directly to R2. Now let's look at the ICMP time exceeded message type. Time exceeded, which is ICMP type 11, is used in two situations. First, to inform a sender that a router couldn't forward the packet because the IP TTL expired. And the second is to inform a sender that a device had to discard a fragmented packet because not all fragments arrived in time. If a device receives fragments from a fragmented packet, but not all of the fragments arrive, it won't wait forever for the missing fragments. So after a certain period of time passes, it will discard the fragments it received and send this message to the original sender. And the code field is used to differentiate between these two types of time-exceeded messages. Code 0 means TTL exceeded, and code 1 means fragment reassembly time exceeded. And here is the message format. The rest of header section is unused, so it will be all zeros in a time-exceeded message. And the encapsulated data, of course, is the IP header and first 8 bytes of the payload of the packet that caused this message. I'll focus more on this message type in the traceroute video of the course, especially code 0, TTL exceeded. But let me briefly explain a couple points. Before a router forwards a packet, it decrements the TTL by 1. If this would result in a TTL of 0, the router will discard the packet. It will not forward it. So if a router receives a packet with a TTL of 1 and it must forward the packet will be discarded. However, if a router receives a packet with a TTL of 1 and the destination is the router itself, it won't discard the packet. It will receive the packet for itself. This is because the router won't decrement the TTL when it receives the packet, only before it forwards it. Here's a quick demonstration. PC1 sends a packet destined for PC3 with TTL2 to R1. Note that no device will use a TTL of 2 by default for its IP packets. But perhaps, for testing purposes, PC1 is sending a traceroute to PC3, or did a ping command with a low TTL. Then, R1 decrements the TTL to 1 and forwards it to R2. R2 then wants to forward the packet, but that would result in TTL 0, so R2 discards the packet. It then sends an ICMP time exceeded message to PC1. Okay, that's how ICMP time exceeded messages work. Note that you can't disable these messages in Cisco iOS. They are always enabled. Now let's look at the final message types for today: echo request and echo reply. Ping uses these two ICMP message types: echo request, which is type 8, and echo reply, which is type 0. If a host receives an echo request, it should send an echo reply back to the source of the request. I don't think I have to demonstrate that. You should know how pings work by now. The code field of these messages should be 0. And here's the message format. Let me explain the identifier, sequence number, and payload. The identifier is used by a device to keep track of pings it sends. And this value is incremented by 1 for each series of pings sent. Note that this is not per echo request, but per ping command. On Cisco iOS, for example, the ping command by default sends 5 echo requests. All of those would have the same identifier. For example, if you ping 8.8.8.8, that will send 5 requests with identifier 0. Then, if you ping 1.1.1.1 after that, it will send 5 requests with identifier 1, etc. And the reply messages will use the same identifier as the request messages. Then, the sequence is used to keep track of each request and reply exchange in a series. So let's say you ping 8.8.8.8 and send 5 echo requests. Request 1 will have sequence 0, and so will reply 1. Request 2 will have sequence 1, and reply 2 will also have sequence 1, etc. It should match between each request and reply. Then, the payload, as I mentioned before, is usually just a string of ASCII characters with no particular meaning. However, the payload of the request must be sent back in the reply. It must be the same payload. But a ping can be sent with no payload. Then the message size will be 28 bytes, 20 for the IP header, and 8 for the ICMP header. In this case, layer 2 will have to add 18 bytes of padding, because the minimum Ethernet payload size is 46 bytes. Let's examine those identifier and sequence numbers. From a Cisco router, I pinged 8.8.8.8 with a repeat count of 3, sending 3 requests and receiving 3 replies. Notice the ID for all of the messages is 0, hexadecimal 0000. The sequence output might be a bit confusing. I'll explain it in a second. For now, just look at the number on the left. 0, then 1, then 2, for the first, second, and third exchanges. Then I pinged 8.8.8.8 again. The ID this time is 1, but once again the sequence is 0, then 1, then 2. Then I pinged another destination, 192.168.12.3. The ID this time is 2. Once again the sequence is 0, 1, 2. Now let me explain why the sequence number is displayed like this in Wireshark. The sequence can be interpreted as BE, big endian, or LE, little endian. And Wireshark displays both, BE on the left, LE on the right. That's why we see two numbers there, 0/0, 1/256, and 2/512. They differ in the order groups of bits, for example bytes, are represented. In BE, the most significant are represented first, and in LE, the least significant bits are represented first. Let me demonstrate with a simple example. The sequence number is hex 0002. In BE, the values are represented in that same order, 0002. The digits on the left are the most significant. They have the largest value. For example, hex 1000 is 4096 in decimal, whereas hex 0001 is just 1 in decimal, because the values on the right are the least significant. They have the least value. LE simply stores these bytes in a different order, like this, hex 0200. If we convert that to decimal, it's 512. Notice in those pings that the third exchange is always 2/512. By the way, this is not relevant for the exam. I'm just explaining why the output looks like that in Wireshark. I had never heard of big endian and little endian until I started looking at packets in Wireshark. And by the way, the same is true for the identifier, but Wireshark only displays BE for it in the packet list. If you open a packet and look inside, you'll see BE and LE for the identifier too. Feel free to Google big endian and little endian if you're curious about it, but it's not relevant for ENCOR studies, so don't worry about it. Okay, here's a chart to review the different ICMP messages we studied. I think it's unnecessary to remember all of the different codes, but it's probably a good idea to remember the ICMP message types. I'll include them in the flashcards for review. Finally, let's talk a little bit about ICMP v6. ICMP v6 is ICMP's implementation for IPv6. Note that sometimes ICMP for IPv4 is called ICMP v4 to help differentiate between them. Like ICMP and IPv4, ICMP v6 is an integral part of IPv6. You can't have IPv6 without ICMP v6. ICMP v6 includes message types like Destination Unreachable, Time Exceeded, Echo Request and Reply, etc. It's very similar to ICMP for IPv4, although there are some different messages. For example, NDP, Neighbor Discovery Protocol, uses ICMP v6 for its messages, as you should already be aware from your CCNA studies. Let's look at a few example messages. Destination Unreachable, ICMP v6 Type 1, is basically the same as for ICMP v4. There are some different codes, but the purpose is the same. Type 2, Packet Too Big, is like the needed fragmentation but DF bit was set unreachable message in IPv4. However, IPv6 usually cannot perform fragmentation, so this message is simply used to say the packet was too big. Type 3, Time Exceeded, is the same as IPv4, although in IPv6, TTL is called hop count instead. Then, types 128 and 129 are Echo Request and Reply, ping for IPv6. Then, the next 5 examples are NDP messages. 133 and 134 are router solicitation and advertisement. And 135 and 136 are neighbor solicitation and advertisement. We'll review these in the IPv6 section of the course. And then, in IPv6, redirect is part of NDP, and it uses an ICMP type value of 137. Of course, there are more, but those are some example ICMP v6 messages. Note that ICMP v6 uses a protocol number of 58 in the next header field of the IPv6 header. This is different than the value of 1 for ICMP v4. And finally, here's the ICMP v6 message format. Same as ICMP v4. It starts with type, code, and a checksum. And then the rest of the message contents will vary, depending on the type of message, just like in ICMP v4. Okay, that's all we'll cover about ICMP v6 for now. It's quite similar to ICMP v4, and we'll cover the NDP messages later in the course. Here's what we covered in this video. First, I introduced ICMP. Then, we covered some different ICMP message types. As I mentioned before, there are many more than this, but these are the most common. At the end of the lesson, we also covered ICMP v6, and we'll cover it more when we look at NDP in the IPv6 section of the course. ICMP is an integral part of both IPv4 and IPv6. It plays an important supporting role by reporting errors, testing connectivity, and other functions. Now let's move on to the quiz to test your understanding of some of these concepts. Here's question 1. Which of the following statements about Destination Unreachable messages are true? Select 2. Pause the video now to select your answers. Okay, the answers are B and D. B is correct because, like other ICMP error messages, the ICMP header encapsulates the IP header and first 8 bytes of the IP payload of the original message that caused the error. And D is correct because the next hop MTU field of a Destination Unreachable message is only used with code 4. Code 4 is called fragmentation needed but DF bit set. It's used when a packet needs to be fragmented but can't be because of the DF bit. A is incorrect because the type field doesn't indicate why the packet was dropped. That's the role of the code field. And C is incorrect because it's a value of 3 in the type field, not the code field, that indicates a Destination Unreachable message. Okay, let's go to question 2. When a router sends an ICMP redirect message, what happens to the original packet that caused the router to send the redirect message? Pause the video now to select the best answer. Okay, the answer is B. The router will forward the packet to its proper destination. Here is that same diagram and explanation from earlier. Note that in the payload of the ICMP redirect message, the IP header and first 8 bytes of the original message will be sent back to the original sender, so C is partially correct. However, B is a better answer, because as shown in step 2 of this diagram, R1 will forward the entire original packet toward the destination. Okay, let's go to question 3. PC1 sends a packet to destination 192.168.12.2. The TTL is 2 when PC1 sends it. What will R2 do when it receives the packet? Pause the video now to think about the answer. Okay, the answer is C. R2 will receive the packet. When PC1 sends the packet, the TTL is 2. When R1 forwards it to R2, R1 will decrement the TTL to 1. If R2 had to forward the packet, it would not be able to, because that would result in a TTL of 0. However, in this case, the packet's destination is R2 itself. So, R2 can simply receive the packet. No need to decrement the TTL. Okay, let's go to question 4. You reload R1, a Cisco iOS router, and issue the command ping 8.8.8.8. You then issue the ping 8.8.4.4 command, followed by the ping 1.1.1.1 command. What will be the values of the identifier and sequence fields of the last ICMP echo request of the last ping? Pause the video now to think about the answer. Okay, the answer is A, identifier 2 and sequence 4. Here is a Wireshark capture. Notice the ID of 2 and sequence of 4 for the final request. These numbers start counting from 0, so the first ping will have an ID of 0, the second 1, and this third one 2. And within each of those pings, the sequence numbers will start from 0 and count up. Cisco iOS devices send 5 echo requests by default, so the last request will have a sequence number of 4. Okay, let's go to question 5. Which of the following ICMP v4 messages is not included in ICMP v6? Pause the video now to think about the answer. Okay, the answer is D, fragmentation needed, but DF bit set. Note that this is a type of Destination Unreachable message, but it's more specific, so D is a better answer than C. ICMP v6 does include other types of Destination Unreachable messages. ICMP v6 doesn't include this type because IPv6 packets are usually not fragmented. So to replace this message, ICMP v6 uses the packet too big message, which is ICMP v6 type 2. Okay, that's all for the quiz and this video. I hope it was helpful. Thanks for watching. Before finishing this video, let me thank my JCNP level channel members. To become a member, please click the Join button under the video. Thanks to Yonatan Makara, Velva Jacob, George Streeter, Funny Dart, Nisir Chowdhury, Devin Suku, Gustavo B.R., Gerard Baker, Marcel Lord, Pavel M., Mr. Erlison, Dragos Hirnea, Zakib Shah, Mayor Salman, Mason Anderson, Vitaus194, Gina Lindley, Mark Jackson, Bold1C1U, Michael Carroll, Gerald Guillaume, Gabriel Braga, Renan Marias, Hector Hernandez, Maratuba, Roji Kuriakos, Arpad Konives, 5 Feet, Owad, Daniel Brown, Tricky Mickey 123456, Scott Thompson, Jose Alvarez, Kevin Hayes, Hussein Yavuz, Samuel Tavares, Mustafa Ersoy, Dear Diso, Nasser Zahar, Alexandru Badic, Brian Grant, Georgi Gemejev, Dibya Swain, Arlen Plagaria, Adelson Pereira, Farad69, Lucian Stoichitoyu, Madmark 50484, Sean Powell, Alexandru Stratan, Hiago Bikalho, Pradeep Halder, Piotr Kaimov, and Abubakar Berry. Sorry if I pronounced your name incorrectly, but thank you so much for your support. Thanks to you and my other supporters, I am able to make these videos and release them for free on YouTube, so I really appreciate the support. Another great way to support the channel is to like the video, leave a comment, subscribe, and most importantly, share this video with others. So, if this video was helpful, I'd appreciate it if you did any of those. Thanks for watching.